So what I did on this example right here is I took all of the population, which again, remember were the four shoe sizes, 8, 9, 11, and 12, and I wrote down every possible sample of size 3. So it is possible if you got 8 and you put it back, you could get 8 again and you put it back and get 8 again. That is one possible sample. So obviously the average of that would be 8. I could also have a sample of 8, 8, and 9, or I could have a sample of 8, 8, and 11, and 8, 8, and 12, and then 8, 9, and 8. So I tried to list them so you could see this is just with 4 people in the population. If I did all the samples of size 3, it takes 64 different samples that are possible. And I went ahead and created a histogram of that so you could kind of see the distribution. And by going to 3, it is now perfectly symmetric normal distribution. You can see the bell curve in there nicely. So what happened is it got closer to the normal curve, and now we can use all of the properties that go with the normal curve as far as the percentages and the standard deviations away from the mean, which is really helpful to kind of look at how sample means describe the population. So first, it also suggests that we recreate our histogram from problem number 1 on top of the completed histogram above. I think the emphasis here is to try to show you how that as you increase your sample size, the more normally distributed the graph gets of the sample means. All right, if I remember correctly, we only had 1 in our first bar. We had 1 correct data point that fit in that bar, and then we had, I think, 3 that fit in this one, so I'm just kind of marking off where they are. If you go back and look at the last page, I think we had 6 on this one, so let's see if that's 4, 5, 6. 6 would be up to here. Oop. And then we had 3 in the next 2 classes. So you can see that was our old histogram. I'm just kind of emphasizing it so you can see it. It's obviously, it's more, the larger the sample size, the more normal and the more narrow it gets towards being in the center, or closer to the actual population mean. All right, next it says find the percentage of the 64 means from problem number 6. I guess this again incorrect. I need to update those from that problem that are at most 1 unit away. Again, so we're trying to figure out by taking a size of sample 3. Last time it was about 65% accurate, if I remember, from up there at the top, or 67%. Now I want to see how accurate these sample means are. So anything between 9 and 11 is considered a good sample. And it's probably easier to use these since I lined them up already right here. So anything from, that's kind of convenient, cut it off right there, that 9. So all of these count. And this entire category counts. All of those are at most 1 unit away from the true population mean, which is 10. I'm trying to figure out which numbers are close to 10. And then it looks like on this one, all of these down here would count all the way up to 11, we said, right? Anything up to 11 counts, so all of these count. So if I look carefully at what I have here, if there's 16 and I didn't count 3 of them, that means 13 of those in that class worked. All of these in that class worked. And again, it looks like 13 of those worked right there. So if I carefully add those together, that's 26 plus 24, which is 50. So in this example, we had 50 good guesses, good samples out of 64. So I want to see if by increasing the sample size, did it increase the likelihood of us getting a good prediction of the population. So 50 divided by 64, it went up substantially. It went up to 78.125, which is, I'll say, approximately 78.1%. So I guess what I'm trying to illustrate here to the best of my ability for you is to show you that when you took a sample of size 2, it was correct 63% of the time. Like, of the samples, there were 10 good samples and 16. So if you randomly made a sample of size 2, you'd get 63% accuracy in making a prediction, most likely with that group. Whereas if we bumped the sample size up to size 3, we'd increase the level of likelihood of getting a good sample to 78%. So as the sample size increases, the probability of you actually picking a good representative sample also increases. So in this one it says, how does this compare? And I got to work on these from the previous example. So I'm saying, how does the 62 compare? And that's what we're saying. As we increased the sample size from n equals 2 to n equals 3, we increased the probability of obtaining a good random sample from 63% to 78%. So we showed in this example that we increased the probability of getting a good representative sample by increasing the sample size. Really, that's the important emphasis for this one. And here it says, what is the mean of the sample means and what is the standard deviation of the sample means of size 3 from that problem number, I think 4 actually, or so it should be, using the formulas mu sub x equals mu and sigma sub x bar equals sigma over square root of n. So let's break that out really quick. So we know that mu, we cheated. We had a population of size 4, so it was easy enough to figure out that that was 10. If the population mean is 10, then the mean of the sample means is also 10. What that basically says, if you took all 64 of those numbers, added all 64 of those numbers together, which are the sample means, divided it by 64, it should be 10. And then the standard deviation of the sample means. We know the standard deviation, I think we calculated it before to be 1.581 if you look on the previous video. That if we wanted to find the standard deviation of the sample mean, so again, if you basically made a huge chart or put all of these in L1 in your calculator and asked it to calculate the standard deviation of all those numbers, that the central limit theorem would help us to suggest that this is equal to this sigma, which is the standard deviation of the population over the square root of n. So we know that sigma is approximately 1.581 over the square root of 3 this time because the samples were of size 3. So we could just type this in, 1.581 divided by the square root of 3. So it's approximately 0.913, or I'll say 0.91. Alright, this is going to come together in just a little bit. Don't worry about it too much. Right now the main focus should be on the fact that we need 3 things from the central limit theorem. So if this is a little too much, I just want to recap the important 3 things. As you increase the sample size of the population, the distribution of the sample means becomes more and more normal. Do you see how it became normal? And the mean of the sample means, so the first thing is it becomes more normal. Second thing is that the mean of the sample means is equal to the population mean. So if you knew every single possible sample, it would have the same as mean of the population. And the last part is that the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of n. All right, describe and compare the frequency distributions between the population and the sample means of size 2 and sample of mean of size 3. That's basically what we just said. We said that it becomes more normal and more narrow. So I guess here's how we could sum it up in a statement. As we increased the sample size from n equals 2 to n equals 3, the distribution became more normally distributed. It became taller and more narrow. And those are kind of the key things. And that happens with any population. Doesn't matter what it looks like. The larger the sample size, the more normally distributed the sample means will be, the taller it'll be, and the more narrow. And it is a little bit high level because we're talking about the distribution of the means and the mean of the means and the standard deviation of the means. So it's kind of a second level. It's a second tier.